Welcome to Physics 30 Prep Fast Track, Lesson 4-3, Conservation of Energy in Springs. In order to move the cart below a distance d from equilibrium, you must exert a force, which means you do work, Fd, on the system. And as we did in the previous lesson, we have derived a formula for the potential energy of a spring. And so the potential energy of the spring is 1/2 kx squared. So when the cart is released, the system oscillates between potential energy. But we'll just look at a simple example of what is the potential energy of a spring as it's moved a certain distance from equilibrium. So in example 1, a cart with a mass of 0.55 kilograms oscillates on a spring with a K value of 25 newtons per meter. What that means is that if you stretch this with a force of 25 newtons, it will stretch 1 meter. So that's the force required to stretch it 1 meter. Now they're asking how much potential energy does it have if we only stretch it 35 centimeters? Well, our formula is 1/2 kx squared. The K value is 25 newtons per meter. The X value is 0.35 meters, which of course is 35 centimeters squared, gives us 1.53 joules. This is the energy of the system, and it will oscillate between mechanical or kinetic and potential energy, both of those types of mechanical energy, as the system oscillates. Another example is a continuation of the first. Now that we've determined what the energy is at 0.35 meters or 35 centimeters, as it comes from this point, 35 centimeters, back to equilibrium, what will be the speed as it passes through that equilibrium point? And it's quite a simple exercise. The first thing, of course, is we calculated what the potential energy is out at 0.35 meters. We got 1.53 joules. Now that we know that it's 1.53 joules, we say that potential at the maximum point turns into kinetic at equilibrium. And since kinetic energy is 1/2 mv squared, solving for v, we take v squared and isolate it by multiplying by 2, dividing by m, and then of course to isolate for v, we take the square root. So v is equal to the square root of twice the kinetic energy over m. Since the kinetic is equal to the potential, then 2 times 1.53 divided by the mass gives you 2.36 meters per second. That will be the speed as it passes through equilibrium. Once it gets beyond equilibrium, it will start to move away from equilibrium again. It will lose some of that speed because it's losing kinetic, because the kinetic is turning into potential. So another example, in this case though, we're not given the mass of the cart. So we're given enough information that we can figure out the mass of the cart if we use conservation of energy. So cart is pulled 35 centimeters from equilibrium and released. The spring constant is 25 newtons per meter, and the cart passes through equilibrium at 5.2 meters per second. What is the mass of the cart? Well, we know from our discussions that since energy is conserved, the maximum potential at 35 centimeters is equal to the kinetic energy at equilibrium. And therefore, since potential is 1/2 kx squared and kinetic is 1/2 mv squared, we can solve for m by dividing both sides by 1/2 or multiplying both sides by 2. That cancels out the halves. And then dividing both sides by v squared, because we want to isolate m. And so when we isolate m, we end up with m is equal to kx squared over v squared. And so k is 25, our x is 0.35 meters, and our speed at equilibrium, according to this question, is 5.2 meters per second. When we square all the appropriate amounts, we get an answer of 0.113, which is in kilograms, and of course 0.113 kilograms is equal to 113 grams. So a simple example of knowing that energy is conserved and using that energy conservation where the maximum potential is equal to the maximum kinetic, and solving for one of these unknowns. And a similar example again, this time they give you a cart with a mass of 0.45 is pulled 42 centimeters from the equilibrium position and then released. The spring constant is 0.15. What is the speed? Again, since energy is conserved, the maximum potential at, in this case, 42 centimeters is equal to the maximum kinetic at, in this case, of course, equilibrium. And they want us, in this case, not to solve for v as we did in the last example, but to solve for v squared. So again, the halves cancel. We multiply both sides, or we divide both sides by m. And in this case, we end up with v squared is equal to kx squared divided by m. And of course, our k value is 15 in this case. Our maximum displacement, 0.42. The mass is 0.45. And we end up with the square root of 5.88, which is 2.42 meters per second. This would be the speed of the cart as it passes through equilibrium. All right, so conservation of equilibrium, or conservation of mechanical energy in springs, is another important concept that you may require in Physics 30. So do lots of practice questions on this particular topic.